All right, let's get started. Today, we're diving into something huge, something really fundamental. We're basically going to learn the language that energy itself speaks. And that language, it's called thermodynamics.
I mean, really think about that. You've got the incredible power of a star, and then you have the complex chemical reactions keeping you alive right now. What if I told you they all play by the exact same rulebook? That rulebook? That's thermodynamics. And today, we're cracking open page 1.
So here's the plan. Think of this as us grabbing the essential tools you need to even start talking about this stuff. First, what even is thermodynamics? Then we'll figure out how to focus on one little piece of the universe at a time. And finally, learn how to describe what we're looking at.
Okay, first up, let's get a handle on what this word even means.
Okay, so what does that actually mean in plain English? Well, it's all about how energy moves around and changes its shape. You know, from heat to motion to the chemical energy in your food. It's pretty much the instruction manual for how the universe works. So here's the thing. The universe is, huge. We can't possibly study all of it at once, right? That'd be insane. So what's the first trick in the book? You draw an imaginary box around the little piece you do want to study. And that's it. That's what a system is. It's just whatever slice of the universe we decide to put under the microscope. It could be tiny, like a single cell, or massive, like an entire planet. The key point is, we draw the line.
So, if that's our system, what about literally everything else? Yep, you guessed it. That's the surroundings. So if your system is a cup of coffee, the surroundings are your desk, the air, you, the whole room.
And this brings us to a super simple but really powerful idea. See, once you've defined this system in the surroundings, you've accounted for everything. There's nothing left over. It's like, here's the thing we're studying, and here's everything it can possibly interact with. Boom. That's the whole setup.
Okay, so we've drawn our imaginary box. The next question is pretty obvious, right? How good is this box? Is it sealed tight, or is it kind of leaky? And depending on the answer to that, we get 3 different types of systems.
First, we have what's called an open system. Think about a pot of boiling water. Super simple. Energy is going in from the stove, right? That's heat. And matter is leaving as steam. So both energy and matter are crossing that boundary we drew. All right, next up is a closed system. This time, picture a sealed water bottle. You can make it hot or cold, so energy is definitely moving in and out. But the cap's on. The water itself isn't going anywhere. So energy can cross the line, but matter can't.
And last, we've got the holy grail, the one that's mostly just an idea, the isolated system. This is like a perfect futuristic thermos. Absolutely no heat gets in or out. And of course, no matter does either. Now, in the real world, a perfectly isolated system is pretty much impossible to make, but it's a really important concept for thinking about the limits of all this.
Okay, quick recap. We know how to pick a system, and we know the 3 ways it can interact with the world. But how do we actually describe the system itself? Like, what are its vital signs at any given moment? Well, we use something called its macroscopic properties. These are just the big picture things that we can actually measure, without looking at individual atoms. Things like pressure, temperature, volume, density, all that good stuff. When you list out these properties, you're basically taking a snapshot of the system. We call that its state. And this state is ground zero for everything we do from here.
All right, we're almost there. One last but super important way to sort all this out. We can take all those properties we just listed and split them into 2 camps. And it all comes down to one simple question. Does the property care about how much stuff you have? Here's the test. It's super easy. If you double the amount of matter in your system, does the value of the property also double? If the answer is yes, we call it an extensive property. If the answer is no, it stays the same, it's an intensive property. Simple as that. Let's start with extensive properties. Honestly, these are the ones that just make common sense. Think about it. You've got a liter of water. It has a certain mass, right? If you add another liter of water, what happens to the mass and the volume? They both double. Of course they do. They're called extensive because they depend on the extent of your system, how much you've got. Okay, now for the other team, intensive properties. And the absolute best example here is temperature. Let's say you have a glass of water that's 25 degrees Celsius, and you have another glass of water, also at 25 degrees. If you pour them together, you don't get 50-degree water, do you? No way! The temperature is still 25 degrees. It doesn't care how much water you have. It's intensive. It's an internal property of the substance itself.
So there you have it. We've just built our basic toolkit for thermodynamics. We know how to define a system, how to classify it, and how to describe its state with properties. But this is all just setting the stage. The real action, the whole point of thermodynamics, is answering the next question. What happens when things change? How does the system go from one state to another, and what are the rules that govern that process? Well, that's where the famous laws of thermodynamics come in. And that is where things get really interesting.